Thanks everyone for joining today, and we will have the NVIDIA Grace webinar, and John Linford from NVIDIA will host that. He's an expert in that and tell us all the secrets. And before we actually get started with John, I want to just show 2 slides, a quick reminder for everyone who has an Ookami account of how you can use those nodes. And you will find all of that also on our webpage, or you might have used them already. So if you want to use the Grace nodes, we have 2 of them. Those are Grace nodes. So just CPUs, no GPUs. You first log into Ookami as you usually do, and then you can just SSH to them. So either SSH fj-grace1 or to fj-grace2. No need to use Slurm. You can just SSH, and please keep in mind that those both nodes are shared resources. So you don't have exclusive access to them, but you're sharing them with other users who might be on them at the same time. So please be mindful of that. And since I know we also have a few people in the webinar who don't yet have an Ookami account, as a reminder, if you want to get one and if you want to start using the system, you're very welcome to do that. We are an access resource provider. So if you want to have an allocation on Ookami, you can just go to access-ci.org and ask for an allocation there. As a reminder, there is no cost associated with that, so you can apply for an allocation. Start with an Explorer allocation. Normally you get a response within 1 business day, and then we can get started and get you set up on the system. And with that, I stop all the things that I wanted to say and hand it over to John. Thanks, John.
Thanks, Eva. All right, let me see if I can get PowerPoint to cooperate. This is always the fun part. Let's try this one. How's that?
Yeah, looks good, John.
Great. Okay, so yeah, thanks everybody for joining. I'm John Linford. I work at NVIDIA, have done for about 2 years now. I worked at ARM before that. So I've been fortunate enough to work with a lot of these HPC systems based on ARM chips from different silicon providers, different design philosophies. You know, there's been a lot of interesting things that have happened on the road to of HPC and ARM. And today I'm going to really talk about kind of where we are at the moment, and I'll wrap up with some slides that look forward to the future a little bit with things like Grace Blackwell. I'm going to focus on practical advice. So this talk is mostly around how can you develop applications, how can you benchmark performance of NVIDIA's superchips. So this would include the Grace Hopper as well as the Grace CPU only superchip. I won't show a whole lot of application performance numbers, and I'll try to stay away from marketing kind of stuff or competitive positioning, and instead focus on information that hopefully developers will find useful and practical. If at any point you have questions or comments or need clarification, just say so, and I'll pause the talk and do my best to answer. It is kind of difficult to monitor a chat while I'm also running the slides virtually. So if you put a question in the chat, I might not see it initially, but I'll try to read those and answer them towards the end of the talk. So basic agenda, I'm going to start with some recent headlines out of HPC. We've just come off the back of ISC, and there were some really fun announcements for Grace and Grace Hopper there that I'd love to share with you guys. This helps understand sort of why is NVIDIA building a CPU? Why are we building a Grace Hopper superchip? Why does this thing exist? I won't spend too much time here, and I'll switch on to what is a superchip and look at some of the design philosophies around these and how that factors into developing for the platform. We'll get into the software. What does a software stack for a Grace Hopper or a Grace look like? What are the tool chains, compilers, libraries, developer tools, things you might want to know, tools you might find useful. And then we'll look at how can you optimize code for this platform, especially on the CPU side. since optimizing on the GPU side is mostly the same on any platform. GPUs don't much care what the CPU is once you start drilling into GPU performance. And then I will look a little bit at one of the cool features of superchips, which is coherent memory. So Grace Hopper and Grace Blackwell have memory coherence between the CPU memory and the GPU memory. And it looks like unified memory, but it's actually done in hardware. How do you optimize your code for a platform like that? Okay, so let's start at the top here. Basically, NVIDIA, like why is a GPU company building a CPU? And I always hear this question with sort of a smirk on my face because it's really it shows that NVIDIA is not a GPU company. Anybody who thinks we're a GPU company has kind of missed the bigger picture. NVIDIA builds a lot of things, GPUs, CPUs, networking fabrics, as well as an enormous amount of software. So yes, GPUs are obviously critical to NVIDIA, but there's a lot more going on here than just GPUs. It really is an accelerated computing platform company. That's fundamentally what we're trying to do. So things like the Grace CPU and the Grace Hopper superchip, they sit within that context. They're part of the NVIDIA accelerated platform. So you have to think about it from that perspective, right? We're not just building a CPU to take over the CPU market. I actually see that as a total non-goal. We don't want to go defeat the entire CPU market. We want to take over the market of accelerated platforms. And we've seen that this is working really well in HPC. Out of ISC last week, we saw 5 of the top 10 Green 500 systems are powered by the Grace Hopper superchip. We have 76% of the top 500 running with NVIDIA GPUs. So this platform is very well accepted and understood in HPC especially, and Grace Hopper is kind of the thing to use in HPC. About 80% of the Hopper GPUs that we've sold into HPC are in the form of Grace Hoppers. So HPC loves this thing, especially when you're already doing accelerated compute. And you can really see that in the number of systems coming online. This is marketing. This is like, AI exaflops of performance. It's a beautiful chart, but it does send the message, that this platform has got a lot of momentum in the market. And I'm making this point, especially to this audience, because many people on the line have been along with the ARM and HPC journey for some time. You've lived through the Thunder X, the Thunder X2, the EMAG, the Ultra, the A64FX, and you've seen what an ARM commercial flop looks like. So I want to really show you what an ARM commercial success looks like. We're doing, this has been well adopted in HPC and the broader market, and it's a pretty exciting platform from that perspective, which means it has staying power. If you are optimizing for this platform, that optimization effort is going to stick around. Now you can see this especially in Europe. The first Grace Hopper system to be announced was the Alps system at CSCS. This was literally the first one to come out, but shortly after we had Venado and others. 10,000 Grace Hopper superchips in this computer. Very, very powerful. It's 20 exaflops of AI, whatever that means. The fact is, it's fast. But if you look at some of the performance numbers coming off this, the ones I find really interesting are the x86 with H100 versus a Grace Hopper. Because the GPU in this case is the same thing. You've got the same GPU on the x86 side and on the Grace Hopper side. And you can see how we've gained performance, not just from having a different CPU, but actually by creating this accelerated platform that combines CPU and GPU together. That's where you're getting these speedups. Apologies for using the CPU as a baseline here. Again, it's a marketing slide, but you can definitely tell that they're real numbers if you compare the x86 H100 dark green bar with the light green GH200 bar. Now, we have Grace Hopper superchip. That's a CPU plus GPU. We also have the Grace CPU superchip. Grace CPU superchip is exactly the same thing, except instead of putting a Hopper GPU on there, we put 2 Grace CPUs. And in a similar way to how Grace Hopper has been well accepted by HPC, we see the Grace CPU, being well accepted in HPC and the data center at large, mostly because it's extremely power efficient. In terms of raw performance, core-to-core performance, this thing is matching or beating AMD Genoa and Intel Sapphire Rapids on most workloads, pretty much all the workloads HPC would care about, due in large part because of its memory bandwidth. If you've worked with A64FX, you know that 1 terabyte a second of memory bandwidth has been around in ARM for a little while, but this is the first time a CPU that is not overly co-designed for its target market is able to deliver that kind of performance. Meaning if you just run code, you get close to peak bandwidth. You don't have to tune about it and think about it too much, which is really nice. So this has been also a commercial success. We have systems like the Isambard 3 coming on. This is one of my favorite systems to show around NVIDIA because it's got a big old NVIDIA logo on the front of it and no GPUs inside whatsoever. It's a pure CPU system. And I think it really shows how NVIDIA is committed to building not just a CPU, not just a GPU, but actually an accelerated platform where the needs of the scientist, the application, whatever it is, that they need to achieve, that's the concern. So we're looking for, in this case, CPU performance is what's needed. CPU performance is what we deliver, and it has the NVIDIA logo on the front. No GPUs. That memory bandwidth pays off really well for HPC applications. You see things like OpenRadios, for instance, running out of the box on this CPU and getting much better performance and better performance per watt compared to contemporary x86s. They made me take the blue and the red colors off, but for some reason they did let us write the names of the CPU in the fine print below. So the small dark gray CPU is a Sapphire Rapids, the one in the middle is a Genoa, and the green one is obviously Grace. Okay, so that's enough of the high-level positioning, marketing stuff. Let's get into the technical side of this and take a closer look at superchips and get into how do we actually program and optimize for these things. So first, to introduce the concept of a Grace CPU superchip or a superchip generally, let's start with the CPU because the CPU is really where this whole thing begins. So the NVIDIA Grace CPU is an ARM ISA CPU. It has 72 ARM Neoverse V2 cores. These are the same sort of off-the-shelf Neoverse cores that you would get in something like a Google Axion or a Graviton 4. They have 4 by 128 bits of SIMD SIMD that can execute Neon or SVE or SVE2 instructions. And at 3.1 gigahertz, this means you're getting something like 3.5 teraflops of FP64 out of the CPU. Now that number, if you're paying attention, is less than the number you get out of a Genoa. So people might say, so how is it that we can claim to be matching or beating Sapphire Rapids and Genoa? Well, there's a couple of reasons. First, this thing doesn't downclock. You can run it at 100% of all threads doing FMA, and you will still have about 3 gigahertz of CPU clock. Doesn't downclock dramatically. The next reason is we keep our calculations very straightforward here. We're not playing any kind of games with the theoretical peak. You'll find that you can actually get really close to this theoretical peak. If you write a tight assembly loop that drives all the cores, you can get there. So it's a real number. The other thing that makes this really powerful is the on-chip fabric. So this was designed from the beginning to be part of a superchip, meaning it was going to be connected to a very powerful GPU or an equally powerful CPU. Now, we don't want on-chip bandwidth to become a bottleneck in that situation. So the on-chip network is arguably over-provisioned. There's an enormous amount of on-chip bandwidth on here. And that combined with the high single core performance results in a very flat memory hierarchy with a lot of single core or a lot of multi-core performance across the NUMA node. It also enables connections to high bandwidth memories like LPDDR5. So we can drive up to 0.5 terabyte of memory bandwidth out of this CPU. So in at a super chip configuration where you have 2 of these things, you're actually able to drive a full terabyte of memory bandwidth. And the thing that really makes Grace interesting is that we have this NVLink C2C connection coming off the side of it. NVLink C2C is an unfortunate name because it's nothing like the NVLink you get out of a GPU. Marketing just likes to say NVLink, so they said it a lot. This is a different physical connection. It's a different protocol. I can't see any real relationship between NVLink C2C and the NVLink you get out of a GPU. So I usually just call it C2C. The C2C connection has 900 gigabytes a second of bandwidth, and it allows you to connect these two large chips together, not just in a high bandwidth sense, but it also enables memory coherency, which we'll get into in a moment. To be clear, this is round trip 900 gigabytes, so it's 450 each way. So this is how we build these super chips. We've got the Grace CPU with NVLink, and you can stick another CPU on there. You get the Grace super chip, which we would say is more than just two CPUs. I'll explain that in a bit. Or you get the GH200 Grace Hopper super chip. This is the CPU plus a GPU, again, connected over NVLink. Now, let's see. I'm going to skip over some of this and go straight to the NVLink C2C. So the thing that makes this more than just CPU plus CPU or CPU plus GPU is that we have enabled in hardware memory coherency between the memory systems of the two chips. So in a CPU, GPU, Grace Hopper configuration, we have two distinct memory configurations, right? We have two different memory systems. One of them is optimized for the CPU with LPDDR5. One of them is optimized for the GPU with HBM3. The C2C connection enables memory coherency, giving you the impression that you have one memory address or you have one memory system because you, in fact, do have one memory address space. This is essentially what's emulated when you use something like unified memory on an x86 hosted GPU, but in this case, we've done it in hardware with a very high bandwidth connection. So at the end of the day, whether your thread is running on the CPU or the GPU, memory is just memory. You can pass pointers, you can allocate memory, you can move stuff around, you can touch pages, you can do anything you'd like and anything you'd normally expect from a memory system from any part of this chip. And you don't have to worry about copying the memory first or anything like that. It's taken care of in the hardware. This is how, this is really the soul of the super chip. And it creates a lot of advantages for developers, especially if you are bringing applications to the platform that historically they were hard to accelerate with GPUs. So if you already have GPU acceleration in your code, you already have CUDA, malloc, CUDA memcopy, stuff like that, that all works. You don't have to change a single line of code. It's all the same stuff. No difference whatsoever. No, don't restructure, don't do anything. Just compile your code and run it. It will take advantage of the high bandwidth connection between the CPU and the GPU. It will not take advantage of memory coherency between the CPU and GPU. I'll get into that in a moment. Existing GPU applications do tend to run better in this because they have that higher bandwidth connection between the two chips. And non-GPU applications are easier to accelerate because you don't have to think about where is my data allocated? How am I moving data between the two memory systems? You can leave that up to the hardware and the hardware will take care of it. A simple example would be I could have a Jupyter notebook. I could take a Python array declared in something like a Jupyter notebook and I could pass it into a CUDA kernel. If you have an API that would let you invoke CUDA from there, you don't have to think about, am I moving the data to the GPU before it actually gets operated on? The hardware will take care of it for you. So this makes it much easier to port codes. Now, it also enables some new optimizations. We'll talk about that in a bit, where if I do modify the code, I can take advantage of memory coherency. The GPU now has half a terabyte of addressable memory available to it, not just the normal 80 or 96 gigabytes that you would get from H100. So there are especially applications in AI where having a large amount of addressable memory enables better performance. So you do have to modify your code to take advantage of those Grace Hopper specific features, but those modifications tend to be very minor. And if you're already using unified memory APIs in CUDA, you don't have to modify your code. You could for performance, but you wouldn't have to. It would still be functional. I will dive into that more as we go along. I'm starting at the top and I'm working down. Now, I said I wouldn't give a lot of application numbers, so this is one of like 4 or 5 I'll show. The key here is this was a third-party application, a reservoir simulator from Stone Ridge called Echelon, where they wanted to try it on a variety of different NVIDIA GPUs. They also tried it on the Grace Hopper. And for them, just recompile, and run. They weren't tuning for platforms. They weren't changing code. They weren't doing anything. They just build their application and run it. And they have these 10 standard simulations that they run to quantify the performance of their application. The interesting bars to compare here are the yellow and the green. So the yellow bar is a H100 hosted by an Intel Sapphire Rapids. And the green bar is Grace Hopper. And you can see that we're running the exact same code, recompile and run on both platforms, and Grace Hopper is outperforming the x86 hosted Hopper in every case. And this is largely because of the increased bandwidth between CPU and GPU. All right, so that's enough about GPUs. Let's get on to the more interesting things of CPUs. So the Grace CPU superchip is when you take the Hopper GPU and instead of doing CPU, GPU, just do CPU and CPU. In this case, everything about the CPU just goes up by 2. You get twice the memory capacity, twice the memory bandwidth, twice the number of cores. Everything is just doubled. From a developer's perspective, you could think of this as a dual socket system. You can see there's no sockets here, but the way that it's constructed from software looks like a dual socket system. You'll see 2 NUMA nodes, one for each of the CPUs. Now, it's worth pointing out that all the super chips have a standard PCI interface. So any peripheral device that already supports ARM, you could just plug it into these things and use it. Your NICs, you could even attach GPUs, right? If you wanted to visualize or attach an A100 or something like that to this, you totally can. You just plug it in and install the right drivers because it's just a standard ARM CPU otherwise. Now, I mentioned the very high bandwidth on-chip interconnect that you've got in Grace. When you remove the GPU and you don't have that HBM3 anymore, you really have a lot of bandwidth, especially for a CPU system. So if we compare what's available in a Grace superchip with 2 Grace dies on the single superchip, with something like a comparable dual socket x86 server, you can really see how that additional bandwidth is helpful for developers because it flattens out the memory hierarchy. In Grace, you get 1 NUMA node for every 72 cores, 1 NUMA node per die. So you don't have to think about as much about where your threads are located. As long as they are accessing NUMA local memory, you're pretty much fine. And I've run some experiments to convince myself this is true. There are very minor differences depending on which core, which thread lands on, and which memory controller it touches. But we're talking in the order of 3%, probably less than run-to-run variability in any standard loaded system. It effectively doesn't matter. So you don't have to pin your threads. You don't have to think about it. Just make sure you've got thread gangs that are not trying to cross the C2C link, with latency sensitive operations. Just try to keep it inside each NUMA node as you normally would, and you'll be fine. We've had a lot of feedback actually from people porting applications from other systems where the confusing thing to them is that they actually have to take out a lot of the complicated thread pinning and MPI, OpenMP decomposition logic and just simplify it down to threads and ranks. All right, let's look at more at programming this thing. So Grace is a standard ARM CPU, meaning that it implements the basic ARM v8 standard, the SBSA standard. This enables it to run a lot of software out of the box. So like the A64FX and the Ampere Ultra and the Graviton, all these chips, they implement this standard, which means that there's a lot of software which is functional. You don't have to think about will it work or not work. It will work by virtue of the ARM standard. So that's a very strong place to begin with. And it's not dissimilar from what you might have heard from other ARM vendors around how they've enabled their ecosystem is by implementing this standard. Grace takes this a little bit farther because in addition to having the ARM v8 standard, it actually implements the newer ARM v9, which includes a lot of specifications for high performance units like SVE2. So implementing ARM v9, it aligns with what we see the cloud vendors doing, if I'm to be blunt. Most of the commercial success for computing today is happening in the cloud. And most of that ARM commercial success is happening in the cloud. So we want to align with what's happening there because, if you want to build a product that sustains, you should follow the money. I think Dan Reed said something basically like this in his ISD keynote last year. I've heard Dan Stanzioni over at TAC has a great quote. He says, if the cloud won't buy it, you shouldn't either. I think that's absolutely true. So we've made sure that the design philosophies we follow in Grace are well aligned with those mainstream CPUs that we see are gaining ground at places like Microsoft, Oracle, Google, Meta, AWS. Now, on top of that, we add the NVIDIA software ecosystem. And this kind of goes back to the first slide I showed where we've got Quantum, we've got Omniverse, we've got Modulus, we've got AI, we've got all these stuff, right? There's a lot of software in NVIDIA. And by the time you're programming for that NVIDIA software platform, you're actually fairly hardware agnostic. That platform targets x86, it targets ARM, it runs with and without GPUs. And so once you're running at that level, it kind of doesn't matter if you're on Grace or if you're on x86. But that's where you get the most performance, you get the most access to the latest features that we build in things like Grace Hopper, is when you're working with the NVIDIA software ecosystem. So for this part of the talk, I'm going to start with the NVIDIA software ecosystem, how you would write code using our tools here. And then I'm going to walk it down a little bit into the more generic, broader software ecosystem around other math libraries, tools, things you could use if you weren't already using the NVIDIA provided software. So at the NVIDIA platform, there's a lot of focus on language models, programming models, and enabling the developer. So accelerating standard languages like C++ and Fortran. I'm not going to go give the whole standard languages talk here, but we can certainly provide those resources if you're interested. The short answer is we are actively involved in the standards committees for all your major languages, making sure that those languages run well on the NVIDIA kit out of the box without any special caveats or changes to the programming model. It should just be portable and just run. Now, in addition to that, we have directive-based parallelism. So you could do things like OpenMP or OpenACC. And then, of course, if you want to go to platform-specific stuff, you have CUDA, you have intrinsics, you have ARM-C language extensions. All of this is provided right up front in the NVIDIA software ecosystem. It's implemented in our compilers, it's implemented in our libraries. It's there for you. So pick your favorite programming model, basically, and you can get it through the NVIDIA software ecosystem. If you like Cocos or Raja or whatever else, that works fine. You can use our compilers, our libraries, our math libraries, or you can just work straight in CUDA or with OpenMP. It's all good. The easiest way to get started with this in HPC is the NVIDIA HPC SDK. HPC SDK connects all of the compilers, libraries, communication libraries, profilers, debuggers, everything you might need as an HPC developer. And the fun thing about this is that it is the same on x86 and ARM. And not ARM in the Grace sense, but ARM generally. That means that if you are working on an x86, you have a GPU, or you don't have a GPU, you can write an application, and then you can take that application and you can rebuild it on ARM using the exact same tool chain. You can rebuild it on Grace using the exact same tool chain. It's platform portable as long as you're using this to develop your application. So this is a good way actually to get ready for Grace and Grace Hopper. If you wanted to see, does my application work on Grace? Does it work on Grace Hopper? Just try building it with the NVIDIA HPC SDK. Use these compilers and libraries. Porting your application to NVIDIA's software stack is functionally equivalent to porting it to Grace Hopper, because we make sure that everything you can do on x86 or x86 and Hopper, you can do on Grace and Grace Hopper. Some recent updates from the SDK really highlight this. So as of last SC, our 2311 release, this is when we added support for Grace Hopper in all the bundled components, compilers, math libraries, networking, tools, etc. Full support for Grace Hopper. And then we've also added optimizations for the Neoverse V2 core that you get in Grace. So it optimized the vectorizer, applied full support for ACLE intrinsics, system math library functions, optimized memory allocators, that kind of stuff is all in there as of last SC. More recent updates have been integrating our math libraries for CPU called the NVIDIA Performance Library, NVPL. I'll show you details about that in a moment. And our most recent release, which came out this week, has new compiler flags that will enable NVPL linkage for you automatically. It simplifies it. Now, outside of the NVIDIA software ecosystem, if you're back on Grace, we have, of course, the whole broader ARM software ecosystem. And this is where aligning with that commercial success in the cloud makes a lot of sense, because we automatically get not just functional, but optimized builds of all the standard stuff you'd need from an HPC system, especially if you're doing AI. So we've got all your frameworks, applications, developer tools, communication libraries. If you are thinking about Grace or Grace Hopper and asking yourself, I wonder if package X is available, the answer is almost definitely yes. At this point, it's much easier to list out the packages that aren't available on ARM than to list the ones that are. 7 years ago, I actually kept a software census of packages that were available on ARM. And at this point, it's impossible. You'd spend a human lifetime trying to write them down. There's just too much stuff. It's much easier to track the ones that are slow to adopt the platform than it is to track the ones that are there. And this, I think, is extra well understood in HPC. People do, I noticed, especially at ISC, people seem to take it for granted that their software is available on ARM. So it's been fun to see that shift over time. NVIDIA performance libraries. So I showed you the Isambard 3 system, NVIDIA logo on the front, no GPUs inside whatsoever. And we want our software platform to be highly performant on these types of systems. So even CPU-only applications where we need to do BLAS, LAPACK, FFT, random number generator, we don't want to rely on third-party libraries that aren't optimized for our platform. We want to optimize for our platform. So we're developing math libraries that directly target the CPU side of this platform. And they do include the components you see here: BLAS, LAPACK, ScalaPack, tensor math, sparse libraries, sparse matrix operations, sparse matrix vector operations, random number generator, and FFT with the FFTW interface. So our objective is to provide something that's as close as the drop-in replacement for other CPU math libraries as possible. So we implement CBAT, BLAS, API, FFTW API, the netlib BLAS, and LAPACK. You can just mostly link against these libraries instead of an open BLAS or an FFTW, and you get a better performance on the Grace CPU. These libraries have been integrated in the HPC SDK. So if you are using HPC SDK, you can do a -M NVPL flag that's in the release notes, or go read the docs, and that will link in any necessary libraries. So if you invoke a BLAS call, it'll link in the BLAS library, or if you invoke FFT, it'll link in the FFT library. Compiler takes care of it for you, so it's much simpler. And speaking of compilers, we have this NVIDIA compiler, which we optimize and we can tune and tweak and deliver performance for Grace, as fast as humanly possible. But not everybody can use the NVIDIA compiler. NVIDIA compiler optimizes for application performance. We don't assert that you can do everything with it. For instance, I would never expect someone to compile the Linux kernel with the NVIDIA compiler. I wouldn't expect somebody to compile basic libraries that are low-level dependencies that aren't performance sensitive. We don't tune for those, and it wouldn't make a lot of sense to use a high-performance application-focused compiler for that application, for that purpose. So in addition to investing in our own compilers, we have a team of open source compiler engineers that are working on the LLVM, Clang, Flang, and GCC compilers to optimize them out of the open. So this is working with those mainline source code repos out in the public. We have a public NVIDIA branch on LLVM, and we work up there. We commit our changes that optimize for Grace. This is not done in-house and then selectively shipped or anything like that. We work outside of the fence by default. But we want to be able to deliver those patches to our users as fast as possible and not have to wait for the LLVM compiler release cycle. Another reason to try to drive this quickly is that our CUDA compiler can only use a host compiler that's a shipped and tested supported product. I can't ask our CUDA compiler developers to certify the CUDA compiler for something called tip of trunk Clang, right? Like that's not a thing. They need a software widget that they know they can download, test, and validate. So to achieve all of this, we actually take our build of Clang with our own Grace patches, we compile it and we ship binaries, and we call this just Clang for Grace. That's because that's really all it is. It's not a special compiler or anything different from what we're doing outside of mainline LLVM. It's just NVIDIA went that extra mile and built that binary for you, and also for our CUDA team to use. So you can go and get started with this Clang for Grace. It's at developer NVIDIA.com, Clang, Grace Clang. And so if your source doesn't build with, say, the NVIDIA compiler, you could try this next. This would be another good compiler to try on Grace. Oh, I should also say the newer release here, we optimize those binaries for compilation time. Now that might seem like a strange thing to invest in engineering in because you don't compile that frequently, but we are very happy to see that we can make the LLVM compiler about 15% faster when we do some profile guided optimization and use the Bolt optimizer on the compiler binaries themselves. Now, the real advantage here is it opens up optimizations for tool chains like Julia or Numba, where the compilation speed on the back end is actually on the critical path. So this does translate to runtime performance and application level performance, even as we optimize in the compiler binaries. So if you're using something like that, where the speed of the LLVM itself is important, then this is definitely going to have some value for you over what you could get from mainline Clang. Trying to summarize the positioning here, because a lot of people ask, what compiler should I use? The short answer is use the compiler that you're already using. If you're already using NVIDIA compilers, continue to do that on Grace. If you're already using LLVM or GCC, continue to do that on Grace. If you're using another vendor compiler, an iFort, a Fujitsu compiler, then use our vendor compiler, use the NVIDIA compiler. Because those vendor compilers, they're already non-portable, right? You're already going to have to change the compiler flags to move to any other platform. So you may as well move to the other vendor compiler where you'll be at the very edge of performance optimization. Or move to an open source compiler if you choose, that's fine. But that's my recommendation is move vendor to vendor or stick with the compiler you have. Debuggers, profilers, we have all the standard ARM debuggers and profilers, your Linaro Forge, so DDT, MAP, all that stuff works great on Grace. We also have enhanced our own NVIDIA Insight to better support CPUs. So Insight's a fun tool chain because historically it started life as a CPU profiler. It wasn't really well known, but it began as something for optimizing the performance of CPU code. Over time, it evolved into a tool that most people know it as a tool essentially that looks for slow CPU code and helps you move that onto a GPU. Like that's sort of its reason to live, is to get code off the CPU and onto the GPU. But now we're taking a more platform-centric view of this tool, and we started adding back features that optimize for CPU and GPU while leaving the code on the CPU itself. So to that purpose, we've added support for all the performance counters that you get in the Grace CPU. So your computational intensity, bandwidth, instruction mix, all available in the GUI here. You can see, flops per byte in the Insight systems tool. So we're stepping towards something that might enable things like roofline eventually. Certainly you could draw your own roofline from the data that this tool gathers. But it's expanding its portfolio of what it can do on a CPU in terms of profiling. When I'm working with Grace, I usually use a combination of HPC Toolkit, Perf, PAPI. Sometimes I use things like MPIP and Insight. So I've got a toolbox of assorted things that I'll be switching between as I work around. I haven't used map in a while, but I do occasionally run it on Grace just to remind myself that it's there and it works. But that also is another option. All right, let's look a little more at how do we actually optimize port code, stuff like that. Actually, before I go into this, I want to check, is there any questions so far?
Yeah, there are quite a few questions.
Quite a few questions. All right, so let me take a quick look at the text here and let's see here. Is there a tuned BLAS available for Grace? Yes, that's the NVPL. NV BLAS is not the tuned BLAS for Grace. This is an unfortunate naming problem. So there's a thing called NV BLAS, which exists to intercept BLAS calls and dispatch them to a GPU. It's essentially a wrapper around the netlib BLAS API. So if you go try to use NV BLAS on Grace, you're gonna have a bad time because it expects the GPU in the mix. You don't want NV BLAS, you want NVPL. Cool, you've installed NVHPC. Does 4x128-bit SIMD mean that Neon vectorized code would run without performance penalty versus SVE2? Yes, actually, I'll show you a pipeline diagram in a bit, and we'll get into that. You can run Neon code just as fast on Grace as SVE2. Neon has less capability than SVE and SVE2, so it's going to be harder to vectorize some loops. But if it's an FMA, for instance, there's no performance penalty for using Neon. I thought NV BLAS, okay, there's a discussion of NV BLAS, NVPL. Why would NVIDIA develop compilers and libraries for ARM CPUs? NVIDIA's been building ARM CPUs for a lot longer than just Grace. So if you go back in time, NVIDIA had a thing, has had their Jetson boards, Orin boards. NVIDIA has supported the ARM ecosystem well before Grace was a thing. In fact, it was, I want to say 2021-ish. I forget the exact date when NVIDIA announced CUDA support for ARM. So it's been around, well before we were making our own CPUs. And that's just simply because if you look at the market momentum of ARM, it's pretty clear where it's going. You might have seen some announcements from Microsoft Surface about Copilot recently. There's an enormous number of new ARM-based laptops coming to the Windows, users. So we're building for ARM because that's kind of the architecture of the future. I think in the same way the electric cars are going to take over from gasoline vehicles, you're going to see ARM take over from x86. Let's see. OpenACC OpenMP offload should work fine on Grace. The offload is just onto other cores. Yeah. I wouldn't call it offload in that case, but sure. I'll say that OpenMP works great on Grace. Oh, yes, Peter. So I saw your question earlier about the scaling dropping off when you got to 72 cores. So the question was, he benchmarked Grace for multi-threaded computation. Scaling stops when you get past 72 cores. The reason for this is because there's, the two NOMA nodes. And generally speaking, you shouldn't be synchronizing your OpenMP thread gangs across NUMA boundaries. There's going to be some latencies there, and something as lightweight as a thread synchronization operation will suffer from that additional latency. So you really want to make sure that any thread synchronization you're doing doesn't occur over the over that NUMA boundary. And this is not just OpenMP. The same thing would be true for any kind of multi-threaded application. Once you are crossing that NUMA boundary, you're incurring latencies. So it's better to take an approach of, say, some number of MPI ranks per OpenMP or per NUMA domain, and then just divide up the remaining cores by OpenMP threads or P threads or what have you. Start pinning. Within the NUMA domain, you don't really have to think about threading or pinning, but do make sure that you're not crossing the NUMA domain. That's essentially all. So for instance, you could pin one MPI rank to core 0, one MPI rank to core 72, and then you can launch a OpenMP gang of 72 threads, and you don't have to think about where those OpenMP threads are being mapped within that NUMA domain. You could if you want, but you don't have to. Just make sure that they're not mapped onto the same cores. All right, I think I've hit the bottom of the questions for the moment. Are there any more questions? Just using 144 threads will not work. That depends on how you mean work. So if you branch off 144 threads and they don't communicate till the end of the program, sure, that'll work fine. If they communicate frequently, then probably don't do that because you're communicating over a NUMA boundary.
That is weird. I have algorithms where the threads don't communicate at all and they stop scaling after 72 threads. But I don't want to hijack your talk, sorry.
No, it's okay. We could take a closer look at that offline if you're interested. The other possibility is, memory is allocated on a first touch basis. So if you are, if you're allocating memory, say from the thread gang master, and it lands in NUMA node 0, and then you're scaling out to 144 threads, those 144 threads on the other socket will in fact be crossing that NUMA domain to touch the memory which was allocated in NUMA node 0. So you also have to think about which thread touches memory when. But we can go into that offline. I'll have some slides that touch on this topic further on, and if they don't answer your question, then yeah, send me a note. We'll take a look. All right, so I want to start off with an expectation here. So when you're porting code to a new platform, it's good to have a reference point for what you should expect for performance, general experience. And I want to set your expectations fairly high. So in terms of performance, you should expect something like a Genoa or something like a Sapphire Rapids. That's if you run your code and it's performing like a Milan or a Broadwell or something like this, there's a software issue. That's not a hardware issue. There's something's wrong in the software that's caused significant amounts of performance to be left on the table. So you should be getting performance comparable to similar x86 parts. The other expectation is you should expect stuff to just work. We see that most applications just recompile and run on the platform, especially if you're using the NVIDIA compilers on some other platform already. If you're using Clang or GCC on some other platform, there's also a good probability that it'll just recompile and run. If you're using Intel compilers, IBM compilers, Fortran or Fujitsu compilers, you might hit some speed bumps, but that's just part of switching from compiler to compiler. You'll actually have more trouble switching from vendor compiler to some other compiler than switching the compute architectures. That you're not really porting to ARM, you're porting away from Fujitsu compiler, for instance. Most of the compiler flags stay the same. You'll use mCPU equals native, and I've got a slide later on that details this. Signedness of char can change. So on x86, they might have the compiler might assume one signedness of char, and on ARM it might assume another. That's because signedness of char is not specified in the standard, and so compilers just sort of flip a coin. So just be aware of that. If you as a developer have made an assumption around the signedness of char, you need to make sure that you use the appropriate command line option that matches your assumption. Again, this is not an ARM specific thing. It's just, you need to understand what assigned char is and isn't. And then in terms of floating point accuracy, ARM is as accurate. ARM is just as wrong as every other platform from an IEEE 754 perspective. So you will get the same floating point performance on ARM as you do as any other platform from a correctness standpoint. That means your answers will be different. You won't get bit for bit accuracy between two different platforms. That's not guaranteed. But you can do certain command line options, lower your optimization levels to a certain order of operations and things like that, and change your floating point accuracy. But that's always a starting point. Be aware that you will get slightly different FP64 answers when you switch from x86 to ARM, because that's how floating point works. Yeah, so I touched on this a little bit. if you're using a standards compliant multi-platform compiler, you're going to have a great time switching to Grace. Because again, you're not really porting to ARM, you're porting away from the other vendor's compiler. We especially see this in vendor compilers that have been around for a very long time and have made certain accommodations for codes that play fast and loose with language standards. If your code doesn't really adhere to the Fortran standards in particular, you might find that it only compiles with certain vendor compilers. That says more about the standards compliance of your code than the software maturity of the platform. So the first order of business really is to make sure your code builds with a standard compliant multi-platform compiler. This could be NVIDIA, could be GCC, could be LLVM. Those are the household names one. Cray also is a good option here. ARM compiler for Linux, which is really LLVM, is another good option. Definitely use the most recent compiler you can get your hands on. ARM has evolved a lot, but it's still evolving. And especially on the more recently released cores, like the Neoverse V2, there's a lot of optimization work in the recent versions of compilers that you'll want to take advantage of. GCC 12.3 is the first GCC compiler to have the correct cost models and scheduling models for the Neoverse V2 core. GCC 13 and 14 is coming soon. Strongly recommended. Use the latest thing you can get your hands on. Do double check that when you're using a wrapper around your compiler, like an MPI Fort or an MPI CC, that it's invoking the compiler you think it's invoking. I've seen this happen a lot where, you do a which GCC and you see you've got your GCC 12.3, that looks great. But when the OpenMPI was compiled, they included the option to hard code the compiler path in the MPI CC command. And so you're not invoking the compiler you thought you were invoking. Fortunately, just double check. Use MPI CC-show to verify that the thing you want to run is what you're actually running. Log your builds, check your logs, make sure that you're not, especially if you have a build system that's non-standard. There's a lot of these in HPC apps where you're not using a friendly, Auto Tools build system or CMake or something like that. You might have a compiler path hard-coded in there. So just check your build logs. Don't cross-compile. I can't believe I'm still showing this slide, but it comes up often enough that I feel like I still have to. I still run across people who think that they have to cross-compile from x86 to run on ARM, and I have no idea why they think this. But yeah, it's out there. Not true. You should always be building on the native platform. Build natively on Grace if you plan to run on Grace. You can cross-compile. It's a thing that exists, but just don't. It's a much harder way to go about your whole porting process. Just build natively on the hardware. That's the best way to do it. Compiler flags. This is where things get interesting. So most of the work in porting a code from an x86 to an ARM, or even optimizing it for Grace, revolves around getting your compiler flags right. Now, this is especially true for Grace, because as a mainline CPU design, if you get the compiler flags right and you enable the compiler to optimize fully for the ISA and the scheduling model that it has for that core, you'll find that you get a pretty good fraction of the theoretical peak for your application without changing the source. Compilers are really good at optimizing for target platforms. That's why we have them, is so that they can optimize for the code so we don't have to. And the key here is to make sure that the compiler is not having its hands tied in any way when it goes to optimize for Grace. So the first thing you want to do is remove all architecture-specific flags. Get rid of any MAVX, MAVX2, anything that might be x86 or PowerPC or even ARM specific. Just get those flags out of there. Remove any march or mtune flags as well. So these flags have a different meaning on ARM, and I detailed this in another talk that I gave here at Stony Brook a while back. You can go see the slides here at this link if you want to know more about it. But the easiest way to make sure you don't make any mistakes is remove your march and your mtune flags. Just get rid of them. Then, after you've removed your architecture-specific flags and your march and your mtune flags, add back ofast mCPU equals native. So this will crank the optimization all the way up. So be aware, if you already know that your code has some floating point sensitivities, you might not want to start with O-fast, but you can use one of the options further down the slide here. But this is the starting point. Start with at least O something, hopefully an O3 or O-fast, and mCPU equals native. Now you can do things like O3 FP contract equals fast to still get some optimization with it while disabling floating point contraction operations, things like fuse, multiply, add, which are known to have a stronger impact on floating point accuracy. You can even turn contractions off entirely, but always keep that mCPU equals native if you're building on Grace, or at least mCPU equals Neoverse v2. I prefer native because it ports forward, right? You don't have to go back and when you go to Grace Next or whatever other ARM platform you might be building for, you don't have to go and change that flag. You can just keep it native. Grace does seem to benefit from link time optimization more than other CPUs. The architecture in the V2 core is notably more sensitive to executable code locality than some other CPUs. So link time optimization can co-locate executable regions and improve branch prediction inside of Grace. So we do recommend using things like link time optimization and even considering things like like Bolt, the LLVM script, a tool for optimizing co-locating code at compilation time. I mentioned signed char, unsigned char, and then G4chan can also benefit from ethno stack arrays. I think this piece of advice might now be outdated as of GCC 13, but I don't think it'll hurt anything if you want to keep it in there. Now I want to explore this a little bit more. Again, I've talked about this at other places, but if you haven't heard it before, this is the one thing that shoots people in the foot when it comes to performance on Grace, so it's worth repeating. march, mtune, and mCPU flags. Now, if I didn't know anything about the way GCC compilers worked, and you showed me these three flags, march, mtune, mCPU, and you said, which one of these generates the most optimal binary? I would intuitively say, well, the mtune equals Neoverse v2 looks like the one that would be most optimal. It says right there, tune, right? It's going to tune for Neoverse v2. Well, unfortunately, that's not really what it means. If I provide an march flag, I'm telling the compiler what ISA is available to the compiler. That's just the list of instructions the compiler is allowed to generate. But it doesn't tell the compiler anything about how those instructions, how much those instructions cost on the target platform. So it's the menu of options available to the compiler, but it doesn't say anything about the prices on the menu. This is one of those menus you get at those tourist traps where you have no idea what you're paying until the final bill shows up. So it's not optimal. Use march to specify architectural features, but it doesn't do anything really for performance except enabling different instructions. And you can see this if I try to compile something like an atomic add fetch instruction. Doing an march arm v9-a, I do get the expected atomic add instruction because the compiler has been permitted to issue this instruction, but the architecture it's tuning for is a generic arm v9. It doesn't understand any of the additional extensions available in Grace, and it doesn't understand the cost model or the scheduling model in Grace. It's targeting a generic, sort of best guess kind of architecture. mtune equals Neoverse v2 will enable the scheduling model and the cost model for Grace, but not the architecture. So the compiler assumes a generic ARM v8 architecture, which is like the least common denominator for all ARM CPUs. This means that instead of getting the nice atomic add instruction we expect, the compiler is not permitted to generate these instructions because they're not part of the ARM v8 base common standard. So we actually get a call to another libgcc function, which is going to be a branch instruction, and then who knows what's happening inside that library. I promise you it's more expensive than a single instruction. So this, in fact, is the least optimal of all options. The most optimal is to use mCPU equals native or mCPU equals Neoverse v2, because this simultaneously enables the ISA for Grace and the cost and scheduling model for Grace. So you can see the correct ISA is generated up there. We have the ARMv9 ISA plus all the extensions, things like the I8MM, which is a low precision integer matrix multiply operation. Very nice to have. bfloat 16 is allowed. Random number generator extensions are allowed. So the compiler has a much broader menu of instructions it can generate, which will enable better optimization and code transformation. And it also has the right scheduling and cost models for the target CPU. So this is in fact the way you get good performance out of Grace. Just use mCPU equals Neoverse v2 or mCPU equals native. The next way to get good performance out of Grace is to link optimized libraries. So for math, your BLAS, LAPACK, FFT, use NVPL. I've shown one way that you can link the NVPL here. If you were using, for instance, the GCC compiler, just link it as you would any other library. Caps L to the destination, lowercase l to the library you want. The libraries come in different flavors. So take our BLAS library, for instance. We have the ILP64 and the LP64 variants. This specifies if you're using 64-bit array indices or 32-bit array indices. You just want to make sure that the library you link here matches the assumptions made in your code. And then you can see that we have the GOMP version and the sequential version. So intuitively, this is with the GNU OpenMP runtime or just no threading sequential laws. This can trip people up. If you already have a code which is OpenMP parallel, and each OpenMP thread is calling a BLAS call, you don't want the GOMP routine. You actually want the serial because the application has already provided that thread level parallelism at a level above the BLAS call. But if you have, say, a MPI only application, you might get a performance bump by running fewer MPI ranks per node and then using the remaining cores as OpenMP threads and linking something like the GOMP version of the library, so that within the BLAS call itself, the matrix operations are parallelized over threads. This is going to vary by application. I can't give general guidance here. You're just going to have to know, what is the right way to invoke BLAS for you and link the right library. So we have BLAS, LAPACK, FFT, random number generator. ScalaPack is included here. Works with HBCX, by the way. If you have single node math operations only, then ARMPL is also a good option. We work really closely with the ARMPL team. In fact, NVIDIA and ARM cross-benchmark each other's math libraries. We have regular benchmarking sessions of ARMPL versus NVPL, and ARM does the same. And then we meet once a month and we just exchange notes so that each of us knows how the other library is performing. This is because ARM and NVIDIA both want Grace to be successful. So I'm happy to say ARMPL is also a good option for math here. Go ahead and use it if that's what you prefer. Now, the other open source libraries, things like OpenBLAS, Bliss, Atlas, we outperform them with NVPL in all cases. I haven't seen any one of these, including things like Eigen, haven't seen them match or beat NVPL. We're usually significantly faster. And that's just what happens when a corporation can invest engineering resources in a piece of software, right? It's just highly optimized for Grace. So if you're using OpenBLAS, an easy way to get good performance on Grace is switch to NVPL. Don't have to change your source code, just change your link line. All right, let's take a look at SIMD. And there's already a question about this with Neon versus SVE. This is a sort of cartoon of the Neoverse v2 pipe. And you can see there's different functional units in here, a couple of branch units, but the interesting ones are the 4 SIMD functional units. So I'll have some slides that'll get into the detail here, so I'll keep this at a high level. The 4 SIMD units all have the same capabilities. You can retire Neon, SVE, or SVE2 in any one of the 4 units. You can run the core at full frequency while running all 512 bits of SIMD bandwidth. You're not going to get any advantages by like saving one unit or avoiding it or anything like that. You should try to drive all of them. Now, because SVE is implemented at 128 bits in Grace, which is the same bit width as Neon, the theoretical peak for Neon and the theoretical peak for SVE, SVE2 is the same. If I had something like a matrix operation and and I wrote it in Neon, and I wrote it in SVE, theoretically, they'll perform the same on Grace. Now we see things can be slightly different in practice. Now, and I do mean very slightly. Typically, Neon code and SVE code perform the same on Grace. The differences will come from SVE being more capable, supporting more data types, and supporting more powerful types of auto-vectorization in the compiler. You're more likely to get codes that are branchy or conditional or more complex data access patterns. You'll get them to auto-vectorize with SVE long before they vectorize with Neon. You will still generate 128-bit SIMD instructions in both cases, but it's a difference between 128 bits of SIMD versus a scalar. So this is the advantage of having SVE compared to just scalar and Neon, like you might have seen in, say, a ThunderX2. The other thing we see is in practice, for a lot of microarchitectural reasons, SVE does tend to slightly outperform Neon. So the takeaway here is if you are writing low-level SIMD code and you are using Neon, you're probably okay. You can continue using that low-level Neon code on Grace and getting close to peak performance. But if you are auto-vectorizing a code and you go and you disassemble it and you notice that there's Neon in there, don't panic, that's fine. Neon is not slow on Grace. Neon is the same as SVE on Grace. So it doesn't mean SVE fast, Neon slow. It just means that the compiler decided to generate Neon instead of SVE.
John, there's a question in chat. There's a question in the chat.
Let's have a look. Will the performance decrease when using more than one node? For example, one node, 144 cores versus two nodes with 72 cores.
No, sorry, it's a bit further down about the instruction throughput from Georg.
Oh, what is the maximum IPC of a Grace core? Should be 4. No, is that correct? Let me think about that. Between 4 and 6.
Hi, John. So I'm asking because you're providing a lot of parallelism, instruction parallelism in those parallel pipelines. So if the instruction per cycle limit is 4, that might be a limitation in some contexts. That's why I'm asking.
I've definitely seen as high as 6. I'm not sure what the IPC theoretical limit is.
So actually, John, I had a related question. So I'm actually trying to tune a small matrix multiply, and what you got labeled in green are the SVE or Neon floating point units. Does that mean load store is going through those other pipelines?
So this is why I hesitated when I showed this slide. There are different different instructions will take different pipes. Right. So even though we have the 4 FUs that are functionally equivalent, which pipeline they get dispatched to can be different. So some load stores will happen in the SIMD units. Some load stores will happen in the scalar load store units. I'm trying. So there's like there was an experiment we did recently where we replaced a Neon. What was it? I can't remember the instruction off the top of my head. Sorry, I'm getting in the weeds. The short answer is that you will get some load stores in the pipes in the bottom, and depending on which one they go, might go into the shared load store or just the load or the store.
So if I pick different SVE intrinsics, I could sort of arrange to make sure they go through those load store units rather than clogging up an FP unit? That's
right. So there's a core tuning optimization guide, which is linked in here, and I can send you a link as well, that details exactly, the latency of every instruction, which pipe they go on to, things like that. And it does cover, if you wanted to maximize your IPC, how would you blend instructions?
That would be rock star. Thanks so much.
Mm-hmm. Let's see. As far as I know, I can set the SVE register width to 256 by force and run my SVE the same way with the native 128. Oh, don't do that. So what you're doing, if if you use a flag like MSVE vector bit width or something like that on GCC, you've told the compiler to issue an SVE instructions as if the silicon had 256 bits in the SIMD units. What you're generating is a code which is functionally incorrect on Grace. It doesn't mean it's gluing two units together or being clever about this. You're definitely generating incorrect code, which if it gives you correct answers on Grace, that's just luck. If you force an incorrect bit width on an SVE architecture, you've forced an incorrect code. It doesn't mean that the compiler has somehow constructed a larger vector. Sorry. All right, so if you're porting out intrinsics from other architectures, mostly x86, then there's some tools that can help you auto-translate these. Now, these tools can be really helpful as a starting point for getting your code moved off of x86. They do come with some performance penalty because of, there's not a one-to-one clean translation between any vector ISA, but it is a good way to start moving your code to Grace from another architecture. Skip over this. So to summarize, in how do you program SIMD on Grace for maximum performance? The first thing to do is get your compiler flags right and let the compiler auto-vectorize your code. Now, as I've hopefully convinced you, if you have your compiler flags right and the compiler knows what it's doing, it should be generating a pretty optimal code for Grace. And you don't have to go write a bunch of intrinsics and really micromanage the way that the code runs. That's always a solid starting point. The next step would be to link optimized math libraries. So, never write your own FFT, never write your own BLAS library. Always use the optimized one that's available to you. If you do want to write intrinsics, don't write assembly. Use the ARM-C language extensions, the ACLE. There's an example of it here on the right. And this is a much more portable way to write intrinsics than just inline assembly. It also gives the compiler a little bit of leeway in optimizing the code as it's generated, which is nice. You can, of course, just write assembly, but you really need to know what you're doing if you go there. Not always recommended. All right, so I included a little more detail on the Neoverse V2 core here. I don't usually go to this level of detail, but I know there's people on the line who have this experience, so we'll go for it. So closer look at the Neoverse V2 core. This is, of course, ARM's core. The microarchitecture comes from ARM, not NVIDIA. We work with them, we talk with them, but at the end of the day, this is ARM's microarchitecture, which is good and bad. That means that there's other CPUs out there, like the Google Axion, that uses the same Neoverse V2 core. It's the same microarchitecture. So at a core level, any optimization you're doing for Grace or Axion or Graviton 4 is interchangeable. Does have the 128-bit vector length, does have the 128-bit neon, separate L1 data and instruction caches. You can see here some of the cache details, as well as the private, core private unified L2. Now, the thing to note here is, this diagram stops at L2. There's a good reason for that. It's because ARM, once you hit up L2, that's kind of ARM's, boundary of IP. They expect things L3 and beyond at the SoC level to be up to the partner. So that's really where Grace starts and Neoverse V2 stops. In Grace, the on-chip interconnect and the L3 cache are NVIDIA's design. They're not to do with ARM in any way. That has a couple of practical implications. The first is that the PMU counters for last level cache on Grace actually refer to L2, because as far as ARM knows, L2 is the last level cache on Grace. If you want L3 counters, you get them from the NVIDIA PMUs, not the ARM PMUs. Oops, darn. Sorry, I accidentally clicked a link trying to skip slides. There we go. All right, this is the same thing we just looked at the pipeline here. And right streaming mode, this is a fun one. So if you've worked with A64FX, you might know that you should use these DC ZVA instructions to get optimal stream performance. Fujitsu had a lot of talks demonstrating why cache line pinning with DCZVA was important. You don't have to do that on Grace. In fact, you shouldn't do it on Grace. Grace has a write streaming mode where the core will detect stream-like access patterns and automatically switch into a mode where loads will behave as normal, but writes look up in cache. And if they miss, they write to the L2 or the system memory instead of generating the line fill. So that the behavior of the core will actually switch to favor stream-like workloads versus more random access workloads. And it continues this way, usually until there's a load operation from the same line that was being written by L2 cache. That's a pretty clear indication that you're out of a stream. Or it detects some sort of cacheable write burst that's less than a cache line. A couple of simple examples here. If you just have A is the sum of two arrays, that'll put you into cache mode. But if you have A is A plus another array, it will keep you in non-streaming mode because you're writing to the same cache line. So this is good news for library writers and anybody who really cares about memory-bound application performance on Grace. Don't worry about cache line pinning or really cache line management in any way. Leave it up to the hardware. I did some experiments almost a year ago now, trying to convince myself that this worked better than a human managing stuff. And I'm convinced if you start using DCZVAs or prefetch hints or things like that, you're more likely to shoot yourself in the foot and hurt performance than improve it. There are some rare cases where a prefetch instruction can be helpful, but they're rare. Typically, the core does a good job of recognizing and optimizing for streaming access patterns. And then this is something that no application developer should ever think about, but if you're down in the weeds, it's worth noting. And I'm putting it here because people who care about microarchitectures will be familiar with these ideas. Memory alignment, there's no penalty for unaligned memory accesses in Grace. You can get some penalties if you cross a cache line boundary, like 64-byte boundary. But generally, it's not something you have to obsess over. If you were to do something like a min copy option or a memset operation, here's some advice for optimizing these. Again, don't write your own mem copy or your memset. glibc 236, I want to say, backported memcopy and memset optimized for Neoverse v2. And every version since then has had an optimized version for this core. So don't write your own memcopy or memset. They've already done these optimizations in the system libraries. But you can see some interesting things here, like the DCZVA is useful for setting mem to 0. Right? That just makes sense. You can just zero out cache lines. Also using the non-write back forms of the load pair, stored pair instructions. That is actually recommended on Grace if you're getting out into that. That could also be useful for, so let's say, a very low level implementation of something like a stencil code where you want to operate on pairs of data. This touches on what I was saying earlier about link time optimization. Avoid placing more than 4 branch instructions inside of a 32-byte region. This is just the branch predictor in Grace is a little more sensitive, maybe not as robust as some other cores. So you can get some optimization by avoiding this kind of thing. Again, at application level, don't think about it. This is really for low-level libraries. All right, I'll take a moment. Any other questions here? Oh, here we go. Do non-temporal stores work as usual on Grace? Yes, that's what the write back load pair knows. Sorry, let me go back here. There we go. You can use non-temporals as expected on Grace. They don't really do anything. If you're going to write an optimized stream triad kernel, the core will detect the streaming access pattern, and the non-temporal load store essentially doesn't buy you anything. So you'll get the same performance either way, but they do work that way.
So if I can comment on this, I meant that in a case where I won't be needing that data anytime soon, I don't want it to end up in the cache. I want a non-temporal store so that the data ends up in memory and I have more cache available for the stuff that I read. That was my point.
Oh, I see. Yes. Yep. That's certainly possible. In terms of secure compute, so TPM, secure enclave, there are some secure compute features in Grace, but they're not as advanced as something you might get in AMD. We could go into that offline because this is not something I'm as expert in. I don't fully understand, where these things work well, in part because they require some kernel patches that are still landing in like kernel 6.9, I think. So let's take a closer look at that. But the short answer is yes, the long answer is maybe. Any other questions before I move on here? All right, so for the last part of this talk, I want to, oh, here we go, related. If I could expect to boot a FIPS kernel on one of these. I don't know. I honestly don't know. I'll find out. Understood. So for the last part of the talk, I want to step back a little bit. We've gone all the way down into the depths of the CPU core. I want to take it back to the super chip level and look at what happens when we have CPU and GPU together with coherent memory, because I think this is where things get exciting. This is the the GH200, GB200 design. So to remind, this is what a Grace Hopper looks like sort of conceptually. We have the Grace CPU, it has its own memory system. We have the Hopper GPU, it has its own memory system. They're connected over the C2C link, 900 gigabytes a second. So if you look at the data rates available in the CPU and the GPU memory, you notice some interesting things. The first is the LPDDR5, you either get 500 gigabytes a second with a memory capacity of 120 gigabytes, or you get 375 gigabytes a second with a memory capacity of 480 gigabytes. So that's sort of the two basic flavors of this thing. In both cases, the bandwidth to CPU memory is less than the bandwidth over the C2C link, telling you that the GPU can drive CPU memory at full CPU memory bandwidth. And in practice, we do see that's the case. Let me see if I can pull this up here. Yes. So a GPU doing a stream sort of access of bandwidth bound test. We have a thing called NV bandwidth that does this. Will drive CPU memory at close to CPU memory peak. That is an important distinction from driving GPU memory, right? The GPU memory, HBM3, is much, much faster, has much higher bandwidth than the CPU memory. So the implication here is that if you're going to access that high capacity CPU memory, you're doing it at the cost of some memory bandwidth relative to GPU memory, but you're not doing it at any cost relative to CPU memory access. So just keep that data point in mind. Also be aware of your CPU memory capacity. The high capacity part has a lower memory bandwidth, so the GPU will likewise drive that at a lower total bandwidth. The other thing to note here is the CPU has, the CPU can't drive the GPU's HBM at full HBM speed. The reason we have two memory systems, we have a CPU optimal system and a GPU optimal system, is so that we can optimize the core and the memory together. CPUs, especially the Neoverse CPU, it doesn't have enough concurrency in the core to drive an HBM system. So we can drive the GPU's memory at close to CPU memory rates. The CPU core can only issue so many requests, and they're not bottlenecked by the C2C, they're actually bottlenecked by the CPU's ability to issue requests as fast as the HBM can keep up with them. So we have this coherent memory system combining the two memory systems into one address space, but there are different performance characteristics depending on who's accessing what data, where the data is resident, how the data is being accessed, if it's going through a cache or something like that. So there's a lot of complications here. So what I'm going to approach is more general guidelines for developers than absolute performance numbers in the system. It's very hard to give numbers that are not wrong because there's so many ways that numbers can change depending on the factors. But I'll try to answer specific questions if you have any. So for starters, having a coherent memory system, this is the first time NVIDIA has had a platform where the GPU memory is visible to the operating system. If you use something like a NUMA control -H, you'll actually see GPU memory as NUMA nodes available to the OS. If you do a free -G, you'll see that the total free memory to the OS includes the GPU memory as well as the CPU memory. And you can do really fun stuff like take a CPU-only application, pin the CPU memory into CPU application data into GPU memory, and then the CPU runs with that data resident in HBM. And you can see some, the performance impact of doing something like that. It's really remarkable, but it will work out of the box. You don't have to change code. Just change the memory binding when you run the application. And now, because of this, very low-level coherency that we have between the two systems, you might wonder, how does caching work? If I have, for example, threads on the CPU side and the GPU side, and they're accessing the same data, what actually happens? So this is sort of a summary of the cache coherency from either side. If you're working with, say, a Grace CPU thread is accessing the GPU data, the GPU line is actually cached on the CPU side. So this means that you could have multiple CPU threads, and they are all, or processes or what have you, working on the same piece of GPU data. It will cache on the CPU side and avoid, traversing the C2C link. The cache is coherent with the GPU memory, and any changes to the GPU memory will evict the CPU's cache line. So as long as the CPU is only touching GPU memory and no GPU threads touch it, you will get CPU L3 cache performance from a GPU address, a piece of data with a GPU address. Now, if you flip that and you have GPU threads accessing the CPU data, it again caches on the CPU L3. And this is because in the use cases we've seen, this is the optimal way to do this. Usually a GPU will work most on HBM data. And so if it's reaching into CPU side data, it's sort of spilled out of GPU, right? You think about that common use case of using a very large data set, too large to fit within GPU memory. So what you really want to do is sort of cache on the CPU side, where you have those large L3 caches, and you can hold that large data set in cache rather than trying to pull some subset over into GPU memory, which hopefully at this point is already full. That's why you're out into the CPU memory in any case. The other common case might be small pieces of CPU data. Maybe it's some scattered data structure that moving to the GPU is difficult. And in that case, again, you'd rather just pluck the small piece of data that you need, and not have to try to move some large piece of data onto the GPU, or it's just not going to be as effective from like a paging perspective. So this is how we optimize on that side. A nice effect of this is that if you have a GPU thread that accesses CPU data, and you have a CPU thread that accesses the same data, that data is already in the CPU cache. So you get good performance from codes that are ping-ponging between CPU and GPU on the same data resident in CPU memory. Sorry. So this is just explaining the fact that there is coherency. If I have a CPU thread that accesses a CPU resident piece of data, it just translates directly to CPU data. Same thing with a GPU. But if I access the other chip's memory system, the same translation is done in the same page table. So the practical effect is that if I malloc data, memmap data, use your standard system, POSIX, malloc, whatever, that data is available to the GPU without having to do any kind of CUDA copy, CUDA malloc, anything. It's just available there as part of the page table. Another cool feature here is counter-based page migration. So if the GPU is frequently accessing a piece of data which is resident in the CPU side, the CUDA driver will realize this. It will migrate that page over to GPU memory. The migration is that's permanent until the data gets flushed back out. and the GPU performance will improve. It's a one-way migration, so you're not going to see CPU that is accessing a lot of GPU memory. The pages don't migrate from GPU to CPU. They only migrate from CPU to GPU. So optimizing for this system, what do we want to do? The first thing to do is look at the different APIs for managing data in a GPU accelerated context. One thing I try to emphasize a lot with Grace Hopper is that if you have existing CUDA code, it runs out of the box on Grace Hopper, hopefully faster, certainly not slower. The subtext there is you didn't change your code. You're still using CUDA malloc. So you're not going to take advantage of some of the more interesting features in Grace Hopper, like memory coherency. So if you're using something like a CUDA malloc to manage your GPU data, the data is placed on the GPU with a default GPU page size of 2 megabytes. The GPU only can access it. It's actually not visible to the CPU. It's not been registered with the CPU page table or the coherent page table. It's just on the GPU side. Data is done through the GPU's MMU, and the CUDA driver won't migrate pages or do anything nice for you. It really is the total control paradigm, where as a developer, I've malloced some data on the GPU, and I've asked the rest of the system to just get out of my way and let me deal with this data because I'm the one controlling the data. So this is where most CUDA codes are coming from, because historically it was completely the developer's job to manage and malloc and move data. And if you're still doing that, we assume that you've thought really hard about it and you've probably made the right decision. We're not going to try to change it for you. But you do give up a lot of the nice features in Grace Hopper, like that large addressable memory. It's just not there. So the first thing to do is change maybe CUDA malloc into a CUDA malloc managed. This changes the way the data is handled and the way the data is visible across the system. First, CUDA malloc managed data is allocated at first touch. So if you have CUDA malloc managed and then the CPU initializes the data, be aware that the data is now resident in the CPU's LPDDR, not the GPU's HBM3. The page size will be a mix of whatever's available on the CPU and whatever's available on the GPU. We recommend 64K pages on the CPU, but you can use 4K pages if you must. 2 meg pages on the GPU. So there will be some coalescing or scattering of pages depending on how data is moved between the two, especially if your first touch data is on the CPU side, and then it's going to be primarily used on the GPU side. So there's an opportunity for optimization here. If you as a developer know that you will initialize in CPU, then move to the GPU, there are some APIs that you can use to help inform the CUDA driver of that, and it can make sure that the data migrates appropriately. The data is visible, obviously, from CPU and GPU, meaning this GPU has full access to the entire memory address space and can use the high-capacity memory. The last case here is really system-allocated memory, which is very similar to CUDA malloc managed. A couple of key differences, but programmatically very similar. This is where you would be for legacy applications that have been hard to port to a GPU. Similar, to CUDA malloc managed, you have first touch allocation semantics. Data will be allocated with 64K pages on a CPU, or 4K pages maybe, because it's not, it's system data. It's not going to be malloced into the GPU memory by default. The difference here might be, if you're doing something like the different page sizes which are coming in the 6.9 kernel, but that's a different topic. And again, you can use CUDA APIs to sort of optimize how this data is moved and where it resides for the lifetime of your application. So even though this data wasn't allocated by a CUDA API call, you can still pass those pointers to the CUDA API to optimize the data placement and movement. So looking at those APIs, these are some enhancements to CUDA 12.3, I want to say, definitely as of 12.4 current version, where you can use hints. You can put hints on memory allocations that will help move data and keep it resident in an optimal way. So you don't really have to change your application at a algorithmic level. You just have to put hints around the data that you've already allocated. And this works for system memory, stuff from a malloc, as well as stuff that comes from a CUDA malloc managed. So you might have something like a CUDA memadvise to say that the preferred location of this data is mostly the GPU, or it's mostly the CPU, or it's mostly read, or it's mostly written by. You can say which NUMA node or which GPU device is primarily going to be operating on the data. So this is a way for you as a programmer to optimize that placement, even in a coherent context, without having to change your code, really. You just sort of advise the driver where to put data. All right, so we're coming up on time here. I'll check one more time for questions. Let's see here. If I allocate memory on the CPU and then I do a bunch of GPU operations on it, do I have to explicitly ask it to be moved to the HBM to get good performance, or does it get transparently moved around? It gets transparently moved around. The driver will migrate it to GPU memory for you. It does that based on access counters. If migrating back to the CPU does not work due to lack of access counters, does that mean that NUMA balancing does not work on Grace? No. So this is the migration only applies in a Grace Hopper context with a GPU. From a Grace context, it's just a dual socket, 2 NUMA node basic system. So yeah, you could totally use NUMA balancing on that system if you want. That said, we actually disable NUMA balancing in our systems. We've found that it tends to perform better if we don't do that, but it's not necessarily broken, and it's nothing to do with counter-based page migration.
Okay, thanks.
All right, any other questions?
John, I think somebody earlier asked, would the slides be available?
Oh, yes, absolutely. Yep. Happy to provide the slides.
Thank you.
All right, so I'll wrap up with some conclusions, and then I'll take a few minutes to talk about the future architecture at Grace Blackwell a little bit. So some of the things I want to highlight here, one is that we do see NVIDIA Grace Hopper improving GPU developer velocity quite a bit because of the coherent memory, because of the hardware taking care of your data movement and things like migrating pages from CPU to GPU. It's much easier to port codes that historically were hard to port to a GPU and take advantage of acceleration. Use the compilers, libraries, tools, profilers, debuggers, MPI distros that you're already using. Just keep using the same software stack. Use a recent version of it, as recent as you can get. But as long as you're using a standard compliant multi-platform toolchain, you'll be fine. They all work well on Grace and Grace Hopper. Do expect stuff to work. It's rare that stuff doesn't work. It's very rare the software at this point doesn't have some ARM version somewhere, and that's even true for commercial codes. There's a large number of HPC ISV codes that run on ARM at this point, officially, like as a commercially supported platform. The key to getting good performance on the Grace CPU is getting your compiler flags right. Make sure you're using mCPU equals Neoverse v2 or native. Use compiler auto-vectorization whenever you can. Try to avoid manual vectorization unless you can really demonstrate to yourself that the compiler is doing the wrong thing. Open source compilers and the NVIDIA compilers on Grace do a really good job auto-vectorizing stuff. So it's usually, it's going to be it's going to be hard to beat that performance with manual vectorization. And then when you're tuning for coherent memory on a Grace Hopper, you just use hints on your memory allocators. So use the CUDA managed memory to unlock the additional memory capacity on the GPU side. Older CUDA codes that just use CUDA malloc, they don't have access to CPU memory in a coherent sense. So you will want to update to CUDA malloc managed, and then use the unified memory hints to optimize your data placement and migration for the duration of the application. Now, everything I've shown you here, everything applies to our next generation platform, the Grace Blackwell. So Grace Blackwell, this is a GB200 superchip. I wish I could show you a physical Grace super chip because they're about the size of a large paperback book. And you've seen, they have the chips on top, but they actually have a lot going on the back as well. There's probably as many chips on the underside of one of these as there is on the top. They're completely coated both sides. So it's a very heavy and dense piece of silicon. Again, about maybe like, so let's say like 8 by 10 kind of. Well, a Grace Blackwell superchip is that, but it's the size of like a small computer monitor. It's huge. And it has 2 Blackwell GPUs and 1 Grace CPU. So this is the same Grace CPU you get in the Grace Hopper or the Grace, exact same one. But you have, instead of 1 Hopper GPU, you have 2 Blackwell GPUs. So to give you a sense for the relative performance here, Grace is a reticle-sized die CPU. It's as big as you can physically make a piece of computing silicon with today's processes, and that's as big as it gets, full reticle. Same thing with a Hopper. It's a full reticle-sized die. So we've got equal silicon volume or area for these 2 computing elements. Each Blackwell GPU is 2 reticle-sized dies. So in Grace Blackwell, we're going from a 1 CPU to 1 GPU in die terms, to 1 CPU die to 4 GPU dies. So the amount of GPU compute here is dramatically improved. You have an enormous amount of HBM, much more GPU compute. The whole platform, just on the accelerated side, has gotten a lot more powerful. But from a developer perspective, everything you're doing on Grace Hopper is the same on Grace Blackwell. You'd still approach it the same way. You still program for coherency the same way. You still optimize for the CPU the same way, use the same compilers, libraries, and tools, same stuff. And then, the flagship that we've got out there right now, which is this monster, is when you take a bunch of Grace Blackwells and you tie them together with, a bunch of copper and fiber and millions of dollars. And you get this DGX GB200 thing, 36 Grace CPUs and 72 Blackwell GPUs, all connected with NVLink coherency. So the GPUs all have access to each other's memories. Monster of a machine, but it's out there. It's coming. And again, same way you program it, just Grace Hopper today. So if you're curious about this stuff, you want to mess around with the next generation AI kit, then Grace Hopper is the starting point for that. All right, that's my talk. Let's see, does anybody have any questions? Tony says it looks like a disappointed robot. Yeah. Do you know why NVIDIA didn't choose a NeoUSB 3 microarchitecture or anything newer, mightier than the V2 for the CPU part of the GB200? Yeah, it's a good question. So the release cadences of NVIDIA's CPUs, GPUs, and DPUs are synchronized, but not synchronous, right? They're the CPU and the GPU release on different years. So we had Hopper release, and then Grace Hopper release, and then Blackwell released, and then we have a Grace Blackwell release. So we're sort of zigzagging between the two. So what you're seeing there is just the natural sequence we have between our GPU and our CPU release. When we have a newer CPU, we'll tie it to a GPU. It's just the way it goes. What is the power consumption of a GB200 cabinet? More than I can pay for. I'm not sure exactly, but it's going to be a hell of a lot.
Yeah, that's got to be north of 80 kilowatts. Right.
This, I'm always reminded of freight trains when we start to get into these numbers, because if you've seen freight train efficiency is astronomical. It's like tons of freight moved on, a gallon of gasoline kind of stuff. It's ridiculous how effective those things are. It's a similar concept here. Yes, the absolute cost in electricity is huge, but the efficiency, the performance per watt is equally huge. So at the end of the day, you're actually much more effective. It's very arguable, and NVIDIA salespeople certainly do argue that this sort of architecture is more earth-friendly and green than a lot of the other architectures out there. How is the idle power consumption for Grace? That's a good question too. So we designed for an idle power consumption of I want to say 14% on the CPU side. It's that's going to be what the CPU does when it's doing nothing, and then the CPU and the memory together. Now there's going to be idle power of the CPU, idle power of the GPU, idle power of the module, idle power of the baseboard, idle power of everything, right? So if you grab something like one of the nodes from the CSCS system, one of HPE's four-way Grace Hopper coherent HPC nodes, idle power for that might be higher than you would expect because they've got slingshot NIC in there. They've got all kinds of stuff in there that's going to be idle. So it really depends on, are you asking just for the CPU? Are you asking for the node, for the module, whatever? For Grace itself, the idle power is very low. And we also support letting the CPU idle down while the GPU is very busy. So you can move power between CPU and GPU, which is nice. You could cap power at the module level, again, CSCS and ALPS. I think they're capping their modules at something like 650 watts, or it's less than the kilowatt TDP that you could have. And that's because you really can do the same amount of work with a lower total power envelope if you allow power from the CPU and the GPU to move around depending on what's active. Any thoughts of a desktop package for a Grace Hopper with smaller core count? I think that'd be cool. What can I say? I can't speak to that. Sure, I'd buy one if such a thing exists. It sounds amazing.